So this is our experimental setup that we're going to use to look at interference patterns generated when a laser is shined on a human hair. We have 3 AA batteries that we'll use for power. I've got a switch so I can turn it on and off easily. Some magnets on the back, and there's the actual laser diode itself. 650 nanometer red laser. Just ordered it off of eBay. Drilled a hole in a piece of wood so it could come through the other side. And you'll notice we had magnets. I used those magnets to actually attach a human hair so that it's right in the middle of that laser. The experiments on YouTube and whatnot show taping a hair across a laser pointer and then taping the laser pointer button down. That'll work just fine too. I wanted something that was easily repeatable and I could take to different schools, probably high schools in this case, and make it easy to check 3 or 4 different students' hair. So that's kind of why I got this set up. It's a little more permanent. So right now we're going to use this setup to generate an interference pattern on the wall and take some measurements. So here we can see the interference pattern projected up on the wall. And what we're going to do is mark the center of 5 dark divisions and then take the average, which I think is probably the best approach I've seen out of all of them. So we'll start here. Two, 3, 4, 5. All right. Now we'll turn the lights back on and measure that. So that's going to be about 7 centimeters. All right, we'll take that number back and use that in our calculation. Hey everybody, it's Lou. So we've talked a little bit about measuring the measurement device and how it's set up to work so that it is easily portable to schools. We also talked about, or actually did, the measurement of the interference pattern. But now I'd like to spend a little bit of time talking about how that interference pattern gets created. I have a pretty good visual here from a YouTube channel called Zach's Lab, and I use this with his permission. Now this isn't exactly what we did, but it's called one-slit diffraction instead of putting a hair on a laser. This is just a single slit that creates these interference patterns. What I wanted to show here is not the exact form of these patterns, but the fact that when you have constructive interference, you'll get a bright spot. That in essence, the waves are reinforcing each other and creating a bright spot on the wall. And then where you get destructive interference, where the waves decrease each other's value, you get the dark spots on the wall. That's what this example is supposed to show. And while it's not exactly for the same experiment we did, I think it shows how the waves interacting as they bend around the hair, shows the wave-like properties of light. Now, if we get down to doing some calculations here, let's take our values that we got. So I know my lambda, which is the light wavelength, that's 650 nanometers. So I've got everything expressed in terms of meters, except at the very bottom. The distance to the wall from the hair was 2 meters. The distance of the 4 divisions. So I marked 5 dark centers and then measured from the first marking to the 5th. Those consist of exactly 4 divisions. So that was 7 centimeters. Then I divide that 4 because I want to get the average of those 4 divisions. And then you take the lambda times the distance divided by our total x, 0.07 divided by 4, or the 0.0175, and you get this measurement. in meters. If you multiply that by 1,000,000, I'll actually get microns. So I've got 74 microns here. And an average human hair is between 75 and 100. This kind of leans towards the fine side. Now, I also mentioned that I have a micrometer that measures in hundredths of a millimeter, and it's very difficult to show, but this one measured just a little under 80 microns based on my physical measurement. So I got approximately 80 microns here. So I think that's a pretty fair calculation. This was a calculation that I got from a YouTube channel called Saturday Morning Physics. I think it was University of Pennsylvania that produced it. And the gentleman used this, which I like the taking the average instead of just marking a single division. And I think that worked pretty well. So light is both a wave and a particle. Thanks, everybody. Bye.